Last semester, when we studied matter and its properties, we touched on this thing called the kinetic molecular theory of matter, and that stated that all matter was composed of tiny particles, and those tiny particles were in constant motion. So it's the motion of the particles that kind of defines what type of state they're going to be in, solid, liquid, or a gas. So by the end of this lecture, you should be able to identify the motions of solid, liquids, and gases, write down the 3 assumptions of the kinetic molecular theory as it relates to gases, know these words: elastic collisions, diffusion, and effusion. And the last part, it's an equation. It's not that bad, looks terrible, but you'll be able to do it. So states of matter, we know we have solids, liquids, and gases, and the fourth state, which is probably the most ubiquitous, but we don't really deal with, is plasma. But solids have a definite shape, and they have a definite volume, and they have motion because the kinetic molecular theory says they have to be moving, but they have motion with very, very closely packed neighbors. So they're able to vibrate against each other, but they're not able to move around each other. So we say they have vibratory motion on fixed points. Fixed meaning they can't change position. Since they can't change position, that's what gives them their definite shape and their definite volume. So if we add a little kinetic energy to a solid, we can cause the attractive forces that hold it together as a solid to break, and we turn it into a liquid. So if we were thinking about solid water as ice, as a liquid, and as a vapor. So now the liquid has a definite volume but no definite shape, and it doesn't have a shape because the particles are able to roll around or move around each other. So they have vibratory motion on movable points. So the solids are on fixed, the liquids are on movable. So you can pour a liquid into a container, but if you pour a liquid on the counter, it's not going to keep its shape because those particles are constantly rolling around each other and past each other. If we add more kinetic energy to that liquid, we can overcome all the forces that hold it together as a liquid and turn it into a gas. Gases are defined as having no definite shape, no definite volume. Gases are moving in a constant, random, straight line path, and we'll talk more about the motion of those gases. So the kinetic theory of matter states all matter is composed of tiny particles, and we know what those tiny particles are, and these particles are in constant motion. So kinetic comes from the word kinetikos, which is Greek for moving, and kinetic energy measures the amount of motion of a particle. So when we talk about temperature, we're talking about average kinetic energy. So the more motion of a particle or the particles, the higher the kinetic energy, the higher the temperature, and vice versa. So we've got these 3 assumptions about the kinetic molecular theory as it relates to gases. And the first one is the particle size. And what we're going to see is sometimes gases are referred to something called a point mass. And they're much, much smaller than the distance between them. So they're separated by empty space. And so from that little opener that you did when you had to compress the plunger, you could see that you could compress the gas. You can cram them into a smaller volume because they're mostly empty space. So the particles are much smaller than the space between them. Those particles are moving far too fast, and they're way too far apart to have any attractive forces that could hold them together as a liquid. There's a way we can get them back to a liquid. We'd have to slow that kinetic energy down by decreasing the temperature and then increasing the pressure to push them back together. So any container of gas is mostly empty space. The next assumption is the particle motion. Gas particles are moving in a constant, random, straight line motion, and you can see from this little image here that if you try to follow one of those dots, it's not curving, it's just going in a straight line motion, and it would continue on a straight line motion until it strikes another particle or it strikes the walls of its container. So gas particles move in a constant random straight line motion. And it's referred to as chaos. And you know, when something's chaotic, everything's going everywhere. So they're constantly colliding with each other. Now, chaos is where we get the Greek word for gas. And if you say chaos several times very quickly, you'll see where we get that word gas from. So go ahead and try it. So in these collisions, we have energy being transferred from one particle to the other, but as a sample, no energy is lost. So those collisions are called elastic collisions, where energy gets transferred, but no energy is lost. And this is an assumption, and we usually talk about these things called ideal gases. And so we know that they don't lose energy, because if they lost energy, if they lose their kinetic energy, that means they slow down, and if they slow down enough, they're going to turn into a liquid, and they're not doing that, so we make that assumption that they transfer energy, but as a sample, no energy is lost. Let's talk about their energy. Two factors are going to determine the amount of energy a gas particle possesses. One of it is the mass, and the other is the velocity. And so you can kind of think about that too. In general, the more mass an object has, the more energy it's going to have in terms of potential energy. If you drop a baseball on your foot versus a bowling ball on your foot, the one with the more mass is going to transfer more energy, and you know it transfers more energy because it probably is going to break your foot. And the other one is the velocity. So the faster something travels, generally the more energy it possesses. Here's a couple examples. This is the Graham's Law of Effusion. Kinetic energy equals 1/2 mv squared. Don't worry about that one. But it just says at a given temperature, the kinetic energy of all gas particles is going to be the same. So a smaller gas particle will move faster than a larger one. So if we talk about average or room temperature, we're making the assumption that every gas particle in the room has the same amount of kinetic energy. So if we think about particles having equal mass, what's going to influence the amount of energy they have? So if we have this bullet and we have two bullets, and so someone throws the bullet at you in a drive-by throwing, and it kind of hits you on the shoulder and you're like, ow, versus someone actually, firing the bullet with a gun, even though they have the same mass, the one that's fired from the gun, of course, is going to cause more damage because it's traveling faster. So if we have particles that are traveling the same speed, what's going to influence the amount of energy? So think about being in the parking lot at Target, and a grocery cart comes rolling along and it bumps into you at 5 miles an hour. You just take it and push it aside. But if a car is rolling along and bumps into you at 5 miles per hour, you are going to feel that a lot bit more. So it's the mass in that case. The car has much more mass, even though it's traveling at the same speed as the grocery cart. It's going to cause more damage to you because it contains more energy. So what could we do to make these bullets have equal energy? Since they have the same mass, well, you could slow one down, or you could speed the other one up. Same thing if you have a different mass here. We could make the grocery cart have the same amount of energy as the car. We'd really have to speed it up. Or make the car have the same energy as the grocery cart. We'd have to slow it down. So we see that as a gas particle, the bigger you are, the slower you are. The bigger you are, you have more energy, so you have to have the same amount of energy as a small guy. So the big guys travel slowly, the small guys travel quickly. So if we have two vials of gas, and one of them's chlorine and the other one's ammonia, which one do you think you would smell first? Which one of those gases would travel fastest? Well, we have to look and see which one is smallest. So in this case, you're going to look up the molar mass. So chlorine off the periodic table is 35.5 grams per mole, and we have 2 of them. So that's going to give us a 71. Ammonia is 14 plus 3, which is 17. So the chlorine molecule is much, much heavier than the ammonia molecule, so it's going to travel a lot slower. The ammonia will travel a lot quicker. So properties of gases. Gases have very low densities, and if you remember how density is determined, density is a derived unit, so density equals mass over volume, the mass of the object over the volume that it occupies. And the way you remember that is you love density, see, mass over volume, clever, huh? So that's how it's measured, as mass over volume. And gases are very, very easily compressed. So we know that they're very, very small. And if you look at this first illustration, you can see that we haven't taken any gas particles out or added any to it. We just compress this little piston and push those gas particles into a very, very small space. Liquids, not so much. Liquids cannot be compressed. They can in a laboratory, but under ordinary conditions, we're going to say that they can't be compressed. So liquids cannot be compressed, and the reason is they're very, very closely packed. Remember, gas particles are far apart from each other. Any sample of gas is mostly empty space, and so you can remove that space by compressing those gas particles. So liquids, no, not so much, and solids, not really, because they're very, very closely packed to each other. So that explains this phenomena. So if this gentleman is diving into his pool, and right now as he's traveling through the air, you can see he's happy, he's not in any pain, but what's going to happen once he hits the surface of the water? You're going to hear that splat, and that's that belly flop, and it's going to sting. So it doesn't hurt him as he's traveling through the air because he's compressing the air as he travels through it. So the air particles are far apart, mostly empty space. He's compressing it, and he doesn't even feel it. Once he hits the surface of the water, though, the water is not easily compressed. So he's going to smack that water really hard. You're going to hear that slap. And but he's not just going to stay on the surface, then he sinks. So he's not compressing the liquid, but he's able to sink because remember, the particles of a liquid are able to move around each other. So they're constantly rolling around each other, and they're going to move around him, so he will sink. But that is going to hurt. Now imagine if he overshot, and instead of hitting the water, he hit the deck of the pool. All right, so that's going to cause the most damage because we know that not only does the solid not compress, the solid does not change position. We have those vibratory motion on fixed points, so he's going to hit that, and that's going to cause the most damage to him of all three. So in that opener, we saw that when you push the syringe, that they had equal volumes of air and water. You could compress the syringe with the air. You could get it pretty small volume, but you could not compress the syringe with the water. So why do you think that happened? Well, again, gases are mostly empty space, any sample. And remember, the water has very, very closely packed. So here's a video I want you to watch and take notes on. And we're going to go on to diffusion. And what diffusion describes is the movement of one material through another. So we're talking about fluids. And when people think fluid, sometimes they think it's got to be a liquid. Well, it's not. Fluids can be gases or they can be liquids. And so only gases or liquids are able to diffuse because they can move around each other. So a solid is not going to diffuse through another solid because those particles are in a fixed position. So with diffusion, you're going to have a continuation of diffusion until there's an equal distribution of all the particles in that sample. So if we started with a sample of material that we sprayed into a room at the corner, is not going to stay there. It's going to start to diffuse out. These gas particles are going to strike each other. They're going to strike other gas particles. They're going to strike the walls of the container. And over time, they are going to move about, and they will continue to move about until we have that equal distribution. So the rate that a gas or a liquid diffuses depends on the size of the particle and the temperature of the sample. So the smaller guys, we know, travel faster. And temperature, the warmer your temperature, the greater your kinetic energy, the faster your gas is going to diffuse. So if we have a sample of cold air versus hot air, and we introduce a sample of gas, the sample in the hot air is going to diffuse a lot more quickly because everybody's moving a lot more quickly. So you have those collisions, much more frequent collisions. Particle size 2, we know that in order to have equal energy, a smaller particle has to travel faster than a bigger one. So the smaller you are, the faster you are. So we said gases can diffuse through other gases more easily than liquids through liquids. It has to do with the spacing. Well, actually, yes, the spacing too. So a gas, remember, is mostly empty space, but if you have a liquid diffusing through another liquid, those particles are really closely packed. They can diffuse because if we look at the sample of a liquid and we see how closely packed those particles are to each other, remember they have that vibratory motion on a movable point. So in order to get from one spot to another, let's say we introduce dye to this water, these particles have to start to move around each other. And so it takes longer for them to get from one point to the other. So you know that saying that the shortest distance between 2 points or the quickest way is a straight line. Remember, gas particles can travel in a straight line until they have a collision with their neighbors. So being mostly empty space, they can travel farther before their path is altered. So think about it like moving through a crowd. It's harder for you to get through a crowd than it is to walk through an empty parking lot or something like that. So gases diffuse more easily than liquids. Think about the spacing and the particle motion. Sample gas is mostly empty space, and the particles move in straight line paths, and they move faster. Particles in a liquid are much more closely packed. They move around each other. They move more slowly, and it takes more time because they can't move in straight lines. So in that virtual opener that we did, we had a food dye placed in 3 different containers. One of the containers was very cold water, one was room temperature, and one was hot water. What did you notice about the food dye and the different temperatures, and why do you think that happened? The rate of diffusion here has to do with the temperature. So we're having a liquid diffuse through another liquid. When the temperature was low, we had a low amount of kinetic energy, which means the particles are moving slowly. Room temperature, they were moving a little more quickly, and as we increase the temperature of the water, the particles move more quickly, and so the diffusion happened more quickly. That's something you should have noticed in that opener. So let's do a little review. Here, circle the correct answers, or write the correct answers in your note-taking guide. Do gases have high or low densities? Do liquids diffuse more or less quickly than gases? And can liquids be compressed or they cannot be compressed? Here's a video that I want you to watch, answer the questions. And now we're going to talk about effusion. And so effusion is similar to diffusion because it talks about the motions of particles, but effusion is specifically talking about the motion of gases. And effusion is the ability of a gas particle to pass through a tiny opening. So you see in this illustration here, we've got gas particles in the upper chamber and no gas particles in the lower chamber, and the gas particles can and will start to fill into that lower chamber until it comes to equilibrium, but they have to hit that small opening, right in the center, just the right angle to pass through. So you can see this phenomena, everyday life, when we talk about balloons. And so, there's two different types of balloons. If you go to Party City, you can get a helium balloon, which is filled with helium, supposedly, or you can get those big mylar balloons, those shiny metal ones that last forever. Now, if you get the helium balloon, it's great for a day, and the next day you see that it's not floating anymore. And the reason, helium balloons float is because helium is much, much lighter than what we call air, which is carbon dioxide, nitrogen, and oxygen. So after about 24 hours, that nice balloon is no longer floating. It's probably, flat on the or laying on the ground. But what you notice about it is it hasn't deflated. It's just no longer floating. So what has happened? So the material that makes up the balloon, it's made of latex, and if we could look at it, submicroscopically, you'd see that the latex is made up of material that has really tiny openings in there. So helium being so small, if it's able to strike that opening just so, it can pass through. But things like oxygen, which is our diatomic molecule, or nitrogen, which is another diatomic molecule, those are much, much larger, and they strike the sides of the balloon, and they don't get to leave. It's just the helium. So once the helium all effuses out, then we go from a floating balloon down to one that's not so floating. Now, mylar balloons, that's that thin metal. And so those openings are much, much, much smaller, and so they hold that helium in a lot longer. So you have those mylar balloons probably still from Valentine's Day floating around. The gift that keeps giving. You have to take them out to the trash can and sacrifice them with a pair of scissors to make them deflate. So we didn't do this in the virtual lab, so I'm going to pass on there. Here's another video I'd like for you to watch and to take notes on. And now we're going to talk about Graham's Law of Effusion, and this looks horrible, but it's really not. And what Graham's Law of Effusion looks at is the rate that particles travel and the mass of those particles. So we're going to compare a velocity. So it looks at the relationship between the rate of travel, velocity, and the mass of the particle. And so here's the actual law. The rate of effusion of two gases is inversely proportional to the square root of their molar masses. So what that means is, if we look at this equation, this V1, that's the velocity of gas number 1, and V2 is the velocity of gas number 2. So those are the two gases we're comparing. So it says it's inversely proportional. So we look at the mass of 1, it's going to be in the denominator, and the mass of 2 is going to be in the numerator. So that's that inverse proportion to the square root of their molar masses. So it looks horrible, but all we're going to do is plug stuff in, and I'll show you a kind of a ways to think about this so it's not so bad. So here's a general rule of thumb for assigning values when you're looking at two gases. Always arrange your variables so the larger mass is going to be in the numerator under the radical. So we want to have small mass on top, small mass on the bottom, and large mass on top. Because when you divide a large number by a smaller number, we're always going to get a value that's greater than 1. If you do it in the reverse, you're going to get a decimal value. And so we'll find the square root of a value that's greater than 1. And it's easier to report. Because if you have a value greater than 1, you're going to say gas A is traveling this many times faster than gas B. Otherwise, you'd have to say gas B is only this fraction of a time or slower than gas A. So it's easier to report it as a value greater than 1. So you put the larger value in the denominator, what happens? You come up with a value less than 1 that you have to find the square root of. So what we're going to look at is this example. Ammonia has a molar mass of 17 grams per mole, and hydrogen chloride has a molar mass of 36.5 grams per mole. What is the ratio of their effusion rates? So we're given the molar masses for each. So what this law is looking at, it says that, of course, this is your equality. So your ratio of the rate of effusion is going to equal what's under this radical. So we have molar masses of each. We look at the mass of ammonia and hydrogen chloride. So remember I said arrange your values so that the smaller molar mass is on the bottom, and that'll let you find the square root of a value that's greater than 1. So the smaller molar mass then, which is the 17, would go on the bottom, and the 36.5 would go on the top. So we put 36.5 divided by 17. Follow your order of operations. Divide those out. And then you're going to find the square root of that value. And so we end up with this 1.47. So what that says is that the hydrogen or the ammonia travels 1.47 times faster than the hydrogen chloride. So 1.5 times faster than the hydrogen chloride, and that makes sense because look how much smaller it is. It's like half the mass of the hydrogen chloride. So that's what we would expect. Remember, the smaller you are, the faster you're going to go. So if we were to plug this in, and you can do this on paper and then insert a picture into your note-taking guide. Let's start at the beginning. So we're going to find the one with the lowest molar mass. Okay, so find the smallest. Okay, so we've got 17.0 grams per mole, and we have 36.5 grams per mole. And so this is our smallest. The smallest is going to go into the denominator. Okay, so let's do our radical sign, and we're going to take this smaller value and we're going to put it in the denominator, 17. Larger one goes in the numerator, 36.5, and that's going to give us a value greater than 1, right? So we'll find the square root of that. And I think what it was 2.5 if I remember from the other one. So we're going to find the square root of that 2.5. And it came out to be 1.47, I think. I can't remember from the previous slide. So that's how we're going to plug those in. It's really not difficult. You just plug in your values as you were told. Put the smaller one on the bottom, and it makes it easier to phrase your answer. So we would say then that ammonia travels 1.47 times faster than the hydrogen chloride. And we'll be able to see that too in a lab, a virtual lab that you're going to do. So you're given the molar masses for each. Plug those values into the Graham's law equation. Assign each value a gas value for V1 and V2. So remember, we're going to put our V1, it's the inverse. So if we have V1 over V2 as the velocities, we're going to put V1 in the denominator, smaller one, bigger one on the top. So here's your solving process again, 2.15. And the square root of 2.15 was 1.47. So the ammonia molecules travel 1.5 times faster than hydrogen chloride molecules because they're about half the mass if you compare those masses. So let's try this one. What is the rate of effusion between nitrogen gas and neon? So the first thing we have to do is we have to find the molar masses of each. So remember, nitrogen gas is diatomic, so you need 2 of those. Neon is a noble gas. So we're going to look at the masses of each, and each nitrogen atom has a mass of 14.0 grams. So this one has a mass of 28.0 grams per mole. And the neon off the periodic table has a mass of 20. All right, so we decided the smaller molar mass is going to go in the bottom. The larger molar mass is going to go on the top. So we're going to find the square root of 28 divided by 20. So go ahead and do that. Which means we need to find the square root of 1.4. Whoops. And the square root of 1.4 is about 1.18. And so this tells us that, remember, the smaller you are, the faster you are. Neon travels 1.18 times faster than nitrogen. Not a lot faster, but then look at the masses. There's not a huge difference in their mass either. So solving these problems, most of them that you're going to be given are very, very basic. Just remember what the equation looks like, and if you're given the values for the molar masses, remember the smaller molar mass always goes on the bottom, and that makes you finding the square root of a value greater than 1, and just makes it easier to phrase it that way.